Hi, and welcome to today's workshop on climate change, hurricanes, and health, co-hosted by Colorado State University and Boston University. I'm Pat Kinney, filling in for Greg Wallenius, and I, along with Brooke Anderson, will be kind of co-hosting this event. Before we start, I'd just like to thank a few folks who helped organize the event. Those include Kate Weinberger, who you'll be hearing from, as well as Brooke Anderson, and Greg Wallenius, who put a lot of effort into planning this. Also, the BU School of Public Health, Environmental Health Department, IDEA Hub, and the International Society of Environmental Epidemiology for help in promoting the event. So I'm going to turn it over to Brooke to moderate and introduce the speakers. Brooke Anderson is an associate professor at Colorado State University. She does work on impacts of climate change on health. She, among our community of climate health scientists, Brooke is pretty famous for her doctoral work on nationwide heat and cold effects on mortality. And more recently, she's really developing an innovative program on extreme storms and has developed some useful code that people are starting to adopt. So I think this event is extremely timely, and I will hand it over to you, Brooke.
Thank you so much, Pat. Good afternoon. Thank you to everybody for joining this panel discussion on climate change, hurricanes, and health. This discussion is coming in the context in the wake of a record-breaking hurricane season in the North Atlantic. There were 30 named storms. The satellite image shows 5 of them. Before each hurricane season, there's a dedicated list of 21 potential storm names ordered alphabetically. In the rare case that there are more storms than there are names on this list, up to last year, the convention in the North Atlantic was to use Greek letters instead. This convention had only needed to be used once before in 2005. This previous year, there were so many named storms in the North Atlantic that 9 names needed to be taken from the Greek alphabet. The season included not only many storms, but also some very severe storms. 3 of these storms, Laura, Eta, and Iota, were so severe that the names were retired and will not be used to name future storms. Several of these storms had extreme human impacts in the United States. This map shows all the billion-dollar weather and climate disasters in 2020. And this past year, these included 7 tropical cyclones. Human impacts were also severe outside of the United States for the previous season's Atlantic Basin storms. Hurricane Eta and Iota, for example, were particularly severe in their impacts on humans in Central America. Colorado State University has just released its forecast for the upcoming hurricane season, and again, it is projecting an above average season. This includes projections of having more named tropical cyclones than average, including more major hurricanes, those that are in categories 3, 4, and 5 on the Saffir-Simpson scale. Today, we are excited to host a panel discussion on climate change, hurricanes, and health. Research on this topic requires interdisciplinary collaborations among atmospheric scientists, epidemiologists, and biostatisticians. Our panel today brings together these perspectives. The panel includes 2 atmospheric scientists, Dr. Andrea Schumacher and Dr. James Stone. They will be talking about hurricane exposure assessment for human health research and about how hurricanes and their impacts are evolving. The panel also includes 3 epidemiologists, Dr. Kate Weinberger, Dr. Robbie M. Parks, and Dr. Greg Cohen. They will be discussing how hurricanes affect human health, both on the short and long timescales, as well as their mental health impacts. Finally, the panel includes a biostatistician, Dr. Rachel Nethery. She will be discussing a methodological approach for tropical cyclone epidemiology. We will begin with each of these panelists giving a talk, and then we will have a question and answer session that will be moderated by Dr. Marianthi Kiumorjoglu. As we go through, please include any of your questions in the question and answer box, and then we will be saving all of these for the end for the question and answer session. We will begin now with our first speaker. Dr. Andrea Schumacher is a research associate at the Cooperative Institute for Research in the Atmosphere, or CIRA, at Colorado State University. There, she develops guidance products for hurricane forecasters and studies societal impacts of hurricanes. Her talk today will be on the challenges of working with hurricane data for interdisciplinary health research. Andrea, whenever you're ready.
You're muted, Andrea.
I apologize for that. You'd think I'd have this down by now, but okay, so today I wanted to talk about using hurricane data for health impacts research. Can everyone see my screen okay?
Yes,
okay.
yes.
Excellent. So first, I wanted to give an introduction. My name is Andrea Schumacher, of course, as Brooke mentioned, and I work at the Cooperative Institute for Research in the Atmosphere at Colorado State University. And I wanted to address what gives me the expertise to talk about this topic today. So CIRA is a cooperative institute between NOAA and Colorado State University, and we work mostly with satellite products and looking at giving forecasters helpful tools in order to predict the weather. My focus has always been hurricanes ever since I was in graduate school. And mainly I work on developing forecast guidance products for hurricane forecasters, mostly the type that display or communicate uncertainty. An example here is the National Hurricane Center wind speed probabilities, which is something that I've been working on and updating for the last decade or so. Another area I work on is societal impacts, and more recently working on hurricane risk communication. So, but what really makes me hopefully experienced enough to speak on this today is that I've been working recently with Brooke Anderson on some interdisciplinary work on hurricanes and health. It is my understanding, as I've become to learn more about this field, is that studies in this area can generally be categorized two ways. There's more short-term studies that characterize health impacts by identifying fatalities with a clear link to a specific disaster, like a specific hurricane. This is more like case studies. And then estimating community-wide excess mortality and morbidity associated with hurricanes. And this is more relevant for longer scale studies, particularly those that we would see for climate change studies. So these longer scale studies require a specific hurricane data set that is consistent and comparable across storms, years, and communities. And as hopefully we'll hear in a little bit, Dr. Anderson has developed such a data set, and I think it will be used, has been used by some of the researchers who will be talking after me. So my talk today, I really wanted to focus on the lessons that I've learned as a hurricane researcher working with an epidemiologist on this interdisciplinary work. So I'll focus on two main topics that I personally found confusing about my own field, especially when I sort of look through the lens of others who are not in my field who may be using this data for impacts research. I'll focus on terminology, which is always a great challenge when you're doing interdisciplinary research, and also the data abundance in my field in hurricane research. It may sound a little bit like I'm picking on my own field here, but I think it's healthy to criticize your own methods and data sets from the viewpoint of non-specialist users. It certainly is essential if you're going to be able to do this impacts-based research. So first is terminology. So I'm going to focus on two sets of terminology that's used in hurricanes that may sometimes be a little bit confusing if you haven't heard it a million times, like everybody in my field has. The first is the types of tropical cyclones. And right off the bat, I'm using tropical cyclones instead of hurricanes. It's sort of a catch-all term for any sort of tropical system that has features that are akin to a hurricane. So in different basins, we call hurricanes different things. In the Northwest Pacific, a hurricane is a typhoon. In the Indian Ocean, we refer to it as a cyclone. So this is sort of a nice broad term that sort of catches everything from the lowest end hurricane type disasters, and that's more in the tropical depression stage, through tropical storms, which is the next category, which is 35 knot maximum sustained winds or higher, and then up to our hurricanes and typhoons and cyclones. I also wanted to mention these two guys on the bottom. So as we get a little bit farther away from what we meteorologists would consider a classic hurricane or tropical cyclone structure, as it starts missing these key elements that for us, we can actually name them as a tropical cyclone, we get these sort of hybrid systems. And you might have heard the term a subtropical storm or a subtropical depression, or even an extratropical cyclone. And I feel like it's important to mention this and have people be aware that are using this data, because it may not matter to an impacts researcher whether it's classically a tropical storm or not. Sandy was one of the situations where Hurricane Sandy in 2012, as it was making landfall, it technically lost what the National Weather Service considered a tropical characteristics. But the fact was, it was still a system with rain and wind. All of those impacts, all of those hazards that impact human health remain. And so you might start seeing this distinction that gets made in the meteorological space. And I think it's worth paying attention to, because it does mean that some of our assumptions about the storms might not be quite correct, but it doesn't mean that the tropical cyclone just disappears. So I also wanted to talk about hurricane intensity, and I'm going to discuss it in terms of a tale of two hurricanes. So the metric we use for hurricane intensity is maximum sustained surface wind, which is defined as the highest 1 minute average wind at an elevation of 10 meters with an unobstructed exposure. So what this is looking for is almost a point. It's a very small area in the tropical cyclone wind field where you find a maximum that meets this criteria. And this can kind of be anywhere. We know it has preferential regions pretty close to the eye, like within the eye wall tends to be our highest wind speeds. But in terms of where it is, it may not be so set in stone. But if we look at this case where we have two hurricanes, both have the same intensity of 100 knots. So in this little red area where their maximum winds are, the maximum wind speed there is 100 knots. But the blue area here represents the size of the destructive wind field, we'll just call it for now. So these are the winds that are actually doing damage. And of course, the hurricane on the left, Hurricane 1, has a much larger wind field than Hurricane 2, but they have the same intensity. So I just wanted to highlight that when we're talking about intensity, we want to be careful because it doesn't necessarily give us a good idea of what the actual impacts are, the extent of the hurricane destructive wind exposure that we might need for health research. And just throwing up the Saffir-Simpson scale once again, this is divided up in a way such that our categories are based on this intensity value, this maximum wind speed. So this is something we also want to be careful about, because it also, you might see sometimes that storm surge also gets thrown in, and there's really not a great one-to-one correlation between intensity and storm surge as well. So we just have to be careful that when we're talking about health impacts, what we're really talking about is the hazards, not necessarily these metrics of the storm themselves. And this is just to drive the point home. We have Hurricane Charlie from 2004 on the left, and Hurricane Sandy on the right, and the red is the hurricane force winds. And when Charlie made landfall, it was stronger than Hurricane Sandy. And yet the size of the destructive wind field is much smaller compared to Hurricane Sandy. So once again, intensity does not necessarily correlate directly with impacts. The second sort of trip up sometimes with working with meteorological data is that there's so much of it. There are so many options for any given metric in terms of scales and data limitations. So the official Atlantic hurricane records are available. It's called the HURRDAT2 database, and it's available back to 1851. But this really only includes metrics like we talked about in terms of the storm center and the intensity. Starting in 2004, they started adding some of these wind radii thresholds to sort of give you an idea of the shape of the wind field. But really, it's our longest serving record, but it's not telling us that much about the wind exposure. We do have wind observations that we can use. We have these automated surface observing networks. You might have seen them they have them at airports a lot of the time. We have these finer scale observing networks that some states have, which is called a mesonet. Aircraft reconnaissance for hurricanes, of course. We only have those for landfalling systems and only up until landfall. We don't fly the systems once they move over land, which is the area where we're much more interested in knowing what's going on. And sometimes we have these small sort of research deployments of micro measurements And we also do have satellite-based techniques for determining wind speed. We also have hurricane wind models, which fall into two classes. We have these dynamical hurricane models, which solve for the governing equations of the atmosphere. They're usually run on a fixed grid, it's fixed latitude and longitude, and they have uniform time steps, and they can either cover the whole globe, those are our global models, or they can cover smaller areas, including a hurricane scale model. So dynamical hurricane models are great in that they're actually solving the equations of physics. However, one of the drawbacks of that is that they're computationally very expensive. They take a long time to run. So they are used in operations and also in research in general, but it's important to note that the models that are used for operations change from year to year. We try to make them as best as we possibly can each year. So if you're going to use this for a long-term analysis, you might want to actually approach someone who's working more on the research side, who might be able to provide you access to a fixed model runs. So the other type of model we can use, which is very computationally inexpensive, is a parametric hurricane wind model. And this is basically, we take a hurricane and we describe the main wind field with some sort of simplistic equations, and we do some empirical fitting to values that we've gotten from aircraft reconnaissance, and because we know the general shape of the wind field in a hurricane, and we base some of this fitting on whether the storm is strong or not, how fast it's moving, and where it is. And these models are good in that they're light. We can make lots of model runs. We can store the data. It's pretty easy to do. But we do make a lot of assumptions about the shape of the hurricane that does make it difficult sometimes, or maybe not as accurate as we would like. But they are heavily used in the reinsurance agency and a lot of research, not really used in operations as much. So so those were sort of the overview of some of the biggest challenges I noticed about my field when I sort of looked at it and from the outside. But I would be remiss if I didn't mention a little bit about the current research that I've been working on with Brooke and trying to make some of this hurricane data better suited for epidemiological studies, particularly long-term studies. So Brooke has developed this beautiful parametric wind model that is available for epidemiologists. It also includes data sets of hurricane hazards, which include wind, rain, flood, tornado, and also in our package to help determine exposure metrics. It covers a time period of 1988 to 2018, and it's available through CRAN as open source packages. And so I worked with Brooke in terms of looking at the parametric model and helping decide what we should do in terms of trying to get the most accurate performance we could out of this model. But when we did an error analysis, we found that there were some situations where we had our largest errors, and those were mostly where we had asymmetric wind fields. So some hurricanes, when they move over land, they often sort of start to recurve to the northeast, and instead of being circular or about the center anymore, their wind field expands in one area. So a lot of the time you'll get a very sort of stretched out circle in the wind field as opposed to the circle we had over the water. And this happens a lot when storms are transitioning into that beast of a extratropical cyclone that I mentioned earlier. So here is an example from Ike 2008, which is a great example of this. So this is the winds that came out of the storm wind model, which is the package that Brooke created. And you can see here are actual observations, and pay attention to the blue and black dots. Those are the actual 34 knot or greater wind. These are from ASOS stations where we saw the greatest winds. And you can see that it's just a little bit displaced because this storm is definitely asymmetric on its right side. The wind field has expanded on that right side of the center. So what I'm doing now is looking at some other parametric models. This one is one that's been developed inside the National Hurricane Center to see if we might be able to add some components of this to storm wind model in the future to sort of minimize the errors on these high error situations. And we can see that it definitely shifts where we're seeing the winds to the area that's a little bit closer to where we saw observations of these higher winds. And so hopefully moving forward, we can hopefully incorporate some of this in, which should hopefully only make this health impact research even better. So main takeaways here. Interdisciplinary research has its challenges. Terminology and language is always an issue. Understanding data scales, limitations, it's really something where when you have two people working together from different fields who can communicate, you can get through a lot of these barriers a lot faster. And there's always, I did not discuss just the whole concept of data format differences in software. We use completely different software in the two fields. I had never worked with R in my life, so it's pretty important. And it does take time. It really took me a good deal of time to truly understand that the health data and research problems of interest, what the nuance was there. And so being involved from early on as I was, thanks to Brooke's great planning, gave us time to resolve all these miscommunications and misunderstandings. So that's it.
Thank you so much, Andrea. As a reminder, we're going to be taking all of the questions through the Q&A, which you should be able to find on your Zoom menu at the bottom. And all of those we will cover at the end through a question and answer session. So please include any questions for any of these speakers along the way in that format. Our next speaker is Dr. James Doan. Dr. Doan is a weather and climate scientist at the National Center for Atmospheric Research in Boulder, Colorado. There, he studies extreme weather and climate change. His talk today will be on the changing character of hurricanes and their impacts.
Great. Well, thanks, Brooke. And yeah, good afternoon, everyone. Well, thanks, Andrea, for that great start to the session. So I'm going to build on some of the concepts that Andrea was talking about and look at how some of these characteristics of hurricanes and their impacts are changing. Now, I can't talk about hurricanes without referring to last season. So Brooke already mentioned it was a record-breaking season. I'd like to look at it in terms of the number of days spent within the National Hurricane Center 5-day cone of uncertainty. So I'm sure many of you are familiar with this cone of uncertainty. It's the 5-day forecast location of hurricanes. And this plot here was generated by Sam Lillo at NOAA. So it nicely shows that in last season, Louisiana spent over 3 weeks within this threat zone. Whereas if you look at Florida and the Northeast US, even those locations spent about 2 weeks. So presumably this sustained threat had some impact on systems and downstream to human health impacts. So let's have a look at how hurricanes might be changing. So I'm sure some of you will have seen this kind of figure before. Here we're looking at a time series from 1895 to 2019 of US annual average temperatures. So of course the blue colors indicate cooler temperatures, the red colors indicate warmer temperatures. And on the whole, we have a transition from the left to the right to warmer temperatures. But it's not that smooth. We have red bars in the early period and blue bars in the more recent periods, and that's climate variability. But on the whole, today's hurricanes over on the right are operating in a much warmer world. And this warmer world is thirsty. It demands moisture from our oceans and land surface. So it's also more moist. So it's really inconceivable that today's hurricanes are the same as in the past. So how do we peer into the future then? So we use these dynamical models that Andrew was talking about, but we run them for like 100 years. So what's in these dynamical models? Well, it's basically we write down the equations, mathematical equations for clouds, ocean currents, sunlight, snowpack, and then we divide the Earth up into tiles. Each tile contains these equations, and the tiles all talk to each other. And so we give our simulation a snapshot of what's happening today, for example, outside the window, and then we run it forwards for 100 years, and it gives us a future state of the climate. And as Andrea mentioned, these are very expensive systems, so we have to run it on a supercomputer. There's a picture here in the bottom right. And if we make these tiles small enough, then we can actually capture extreme phenomena such as hurricanes. So this is not a real hurricane, it's one that's simulated in our model. And it's remarkable how realistic it looks. So we can count these things, track them, look at changes in wind speeds, for example. So what are these simulations telling us? So I'm going to tell you a few findings in order of our confidence from the most confident first. So we're very confident that today's storm surge is higher than it used to be, say, in the 1970s for a given storm. And that's because our oceans are warmer, so they occupy a greater volume, so the seas are higher. But also there's been some melting of land ice. We're medium confident that in some regions, tropical cyclone rainfall is heavier than it used to be. So here's an example of Houston from Hurricane Harvey. So Houston is no stranger to extreme rainfall. And in fact, the city of Houston recently quadrupled its estimate of the risk of extreme rainfall compared to the 1970s. And we have fairly good physical understanding that the rate of rainfall increases by about 4% for every Fahrenheit warming. So that's quite well understood. We're getting now into the low to medium confidence that in the future, we'll expect to see stronger hurricane winds. These are the surface winds that Andrea defined. And here's an example of Mexico Beach after Hurricane Michael in 2018. So this may be a sign of things to come. So I like this figure of Hurricane Laura from last year. And hopefully I'm motivated that we're in a new era of hurricanes. So the hurricanes have changed, but so have we. So you can see our population centers there indicated by the lights at night. So our population has increased and we've also migrated, relatively speaking, to the coast. And so if it impacts, of course, it's not just the hurricane that drives damage, it's the population and how vulnerable we are. So how can we think about climate change? Well, we think of climate change then as a pervasive and growing risk multiplier. So all the ingredients have been there historically, but climate change is exacerbating the situation. So what are we going to do about it? Well, I would like to give one example from my own work, and that is building codes. So to illustrate that, I'm using the case of Hurricane Dorian in 2019. It was the strongest landfalling hurricane ever in the Bahamas. I think it was gusting up to 220 miles an hour. Not only that, those winds were sustained for 24 hours. The hurricane basically sat over the Bahamas. So look at the performance of two neighboring structures here. The shell of the building on the left basically survived. The building on the right was wiped clean of its foundation. And this speaks to the strength of building codes. And in fact, we conducted a more comprehensive study using the case of the Florida building code and found that retrofitting structures and building new homes to code reduced average wind losses by about 70%. That's 70. And for every dollar you spend on building to code, you get back $4 in mitigated wind losses. So it's clearly effective policy with presumably health impacts by being able to sustain or create more resilient health infrastructure. Now, I'm glad Andrea brought up Charlie because we're going to return to Charlie now. I'm just making the point here that no two storms are alike. Here we see insured wind losses for two hurricanes that tracked over the Florida Peninsula in 2004. And the black line is the hurricane track. So for Charlie, all the losses are concentrated right along the track, with the hotter colors are the highest losses there over the Tampa Bay region. Contrast that with Francis, where the losses are spread over a much larger area, but it's less intense. The peak losses are lower. So presumably the outcomes are very different here for the two storms. Another point I want to make is that the local weather can be very different from the peak winds and rain. So I'm going to illustrate that back in Louisiana again here. Here you're looking at the surface wind field generated by one of those parametric wind field models. for Hurricane Betsy way back in 1965. So Betsy was almost a Cat 5 at landfall. Whereas if you were in this town of Homer, just a few tens of kilometers inland, you only experienced Category 1 winds. So presumably the outcome would be very different had those strong winds penetrated farther inland. And the same is true of hurricane rainfall. So here's a map of total storm rainfall for Hurricane Gustav in 2008. So the peak rainfall was upwards of nearly 2 feet. Whereas again, if you're in Homer, you only, well, I say only, it's still 5 inches, but you only experience relatively smaller rainfall with presumably vastly different outcomes than maybe what you were hearing in the forecast. So my final point then is that I just want to give an example of how I'm using our understanding of climate change and hurricanes to stress test risk management strategies. So I collaborate a lot with the reinsurance industry. And in those projects, we develop future hurricane scenarios. So on the left is a surface wind field of Hurricane Irma. We're over southern Florida now in 2017. And on the right, I basically inflated the winds by 10%, consistent with our understanding of how hurricanes respond to 2 degrees Celsius of warming. And the insurance company can then take these wind fields and plug them into their loss models and assess whether their insurance portfolios and structures are resilient to climate change. So I think there's a lot of ways we can use this kind of concept, particularly for health application. So I'll leave it there then. So hopefully I'm motivated that we're in a new era of hurricanes. There's no going back. We can think of climate change as a pervasive and growing risk multiplier. And as Andrea mentioned, we really need this deep integration among disciplines to really transform our understanding of the intersection of human health and hurricanes. And
Thank you so much.
Thank you for listening.
Thank you so much, James. As a reminder to everyone, if you have any questions, we'll be taking those at the end. Please go ahead and put them in the question and answer box that you can find on your Zoom menu. Our next speaker is going to be Dr. Kate Weinberger. She's an assistant professor at the University of British Columbia. She studies the relationship between climate change and human health, particularly exposures related to extreme weather events and aeroallergens. Today, she'll be talking about the long-term health impacts of hurricanes in the eastern United States. Kate, whenever you're ready.
Great. Thank you so much for that introduction. Brooke, can you see my screen?
Yes.
Okay, fantastic. All right. Thank you again for everyone who's participating in the panel and to the audience for showing up virtually today. So since I am the first of sort of the health-facing presentations, I'm going to try to do 2 things in my 10 minutes or so. So I'm going to try first to give you just a bit of a general overview of what we think the health impacts of hurricanes might be to try to sort of set the stage for all the talks that are going to follow. And then I'm going to tell you just a little bit about some ongoing work of mine looking at the longer term health effects of hurricanes in the eastern United States. Okay, so I'll start out by talking a little bit about how we think hurricanes might impact health. You're probably getting the sense already from the first 2 talks that hurricanes are really complex events in terms of the risks that they might pose to human health. So some of the health impacts of hurricanes might be due to the physical hazards of the storm itself. So things like high winds, heavy precipitation, storm surge, and sort of the flooding that can follow. But some of the health impacts, also likely arise due to all of the other types of disruption and damage that can occur in the wake of a hurricane or a tropical storm. So for example, some people may evacuate the area immediately before or during or after a storm. And so there may be risks related to injury during the evacuation. And there also may be broader risks among people who are displaced in the wake of a storm. So for example, there could be infectious disease transmission in shelters. Folks could experience interrupted access to key services, in particular to medical care. Other people may remain in the area during a storm and their housing might not be optimal. So people may have lost power as the result of factors including high winds. And so people may not have heat or air conditioning in their homes. They might not be able to refrigerate food. They might not be able to operate home medical equipment. And then people who remain or return to the area might be exposed to all sorts of secondary hazards. So examples of these might be exposure to contaminated floodwater or drinking water, as well as potentially mold growth in homes that were flooded. As people return, there might also be health and safety risks due to cleanup and recovery activities. And then finally, in my list of sort of example pathways, both the storm itself and the disruption that follows could contribute to traumatic or stressful experiences. So what do we know about the health impacts of all of these exposure pathways? Well, many of these exposure pathways we know can result in illness and death either during a storm or within a few days or a week or so following the storm. So sort of short-term impacts on health. So for example, it's fairly well documented that drownings, traumatic injuries, and deaths are elevated during and immediately after storms, potentially resulting from either the physical hazards of the storm itself or evacuation. And in addition to that, there's also some emerging evidence that increasingly points to a broader range of short-term health impacts. So I know my co-panelist, Robbie Parks, who's going next, is going to be speaking about this in much more detail, but I'll give you just one example. This table comes from some work of mine looking at emergency department visits from different types of disease among older adults in the week following Hurricane Sandy in New York City. And what we found in this study was that in the week following the storm, there was an increase not just in the rate of ED visits due to injuries, but also due to a variety of other causes as well, in particular respiratory, cardiovascular, and renal disease, as well as skin and soft tissue infections. So raising the possibility that there are some pathways at play here other than just the physical hazards of the storm itself. In addition to these short-term effects, there is also evidence that hurricanes may affect health over longer time periods. So here I'm talking about months or even years, rather than days or weeks following the storm. There are a number of studies that have provided evidence of a link between major hurricanes like Hurricane Katrina and mental health outcomes. And there's also reason to believe that hurricanes may affect physical health over this time scale as well. So one sort of plausible pathway might be that exposure to mold in homes or air pollution during cleanup activities could result in consequences for people with respiratory health conditions like asthma, and these might manifest over months rather than over a period of days. But the research here is fairly limited, and to date it has focused on specific large storms for the most part, so storms like Hurricane Katrina and Sandy. I'd posit that one avenue we have for expanding research on longer-term health outcomes is to make use of databases that contain longitudinal information on healthcare claims, so administrative data that allows us to follow people over time. And so with the remainder of my 10 minutes, I just want to give you a quick example of the kind of work that can be done using this type of data. Specifically, I'll be talking about an ongoing project of mine looking at respiratory health consequences of hurricanes and tropical storms. So in this project, my colleagues and I are looking at whether hurricanes are associated with increased exacerbation of symptoms among children with asthma in the year following hurricane, so over a period of 12 months. And rather than looking just at one specific storm, we're looking at all storms that occurred in the eastern US between 2000 and 2018. For this project, we obtained information on hurricane exposure at the county level from the R package and data repository called Hurricane Exposure. So this is something that several of my co-panelists and meeting hosts have been leaders in developing. The image on the right here is just showing the tracks of storms that affected the eastern US during our study period. And the other key data source for this analysis is something called the Optum Labs Data Warehouse. This is a longitudinal data asset that includes both de-identified administrative claims and also electronic health record data. For the purpose of this project, we're actually just working with the claims. And specifically for this project, we've used it to identify children who have commercial health insurance who have evidence of an asthma diagnosis in the previous 18 months. Just very briefly, the approach we are following for this ongoing study has 4 major steps. We're beginning for each storm by identifying counties that are exposed to the storm of interest. Our main definition is based on wind speed. Next, we're matching each exposed county to 1 or more counties not exposed to that same storm. We're then estimating monthly rates of symptom exacerbation requiring medical attention among children who have asthma. So here I'm talking about urgent care visits, ED visits, and hospitalizations. And then finally, we're comparing the rate of asthma exacerbation occurring among children in exposed versus unexposed counties and in the 12 months after versus the 12 months before the storm. So some of you may recognize this as a difference in differences design. So this slide is just showing some preliminary results from that analysis. I'm plotting the results from each storm separately, and I know it's very small, so I'm just going to narrate the key points to you. So essentially what we're finding so far is that while there may be some evidence of an increase in symptom exacerbation in the year following the storm for some specific hurricanes, in particular Hurricane Sandy, we're not seeing evidence that hurricanes in aggregate are substantially associated with increases in asthma exacerbation over the long term in this specific population of children with health insurance. But again, I want to flag that this is an ongoing analysis. And so some of our next steps here involve sensitivity analyses where we're looking at varying the time periods and also the storm definition. So in summary, hopefully this presentation has given you a sense of the complexity of hurricanes as an exposure and has also highlighted that they have health effects that may become apparent over multiple timescales. Also hopefully gave you just a little bit of a taste for how longitudinal administrative data might be used to study the longer term health effects, whether those are respiratory effects or otherwise. And I'll just conclude by saying there are, of course, limitations of working with these sorts of administrative data. I think a particularly important one in this context is that it's limited to people who have health insurance. And perhaps this is a thread that we can pick up on a little bit if we have time in the discussion. So I'll just close out by thanking my collaborators on this ongoing work. And I also want to acknowledge that this project has received funding from the Robert Wood Johnson Foundation through its Health Data for Action program. Thanks.
Thank you so much, Kate. Just as a reminder, if you have any questions on this or any of the talks so far, you can put those in the question and answer box, and we'll be taking all of the questions at the end of all the talks. Our next speaker today is Dr. Robbie N. Parks. Dr. Parks is a postdoctoral research scientist at the Earth Institute and Mailman School of Public Health at Columbia University. His research focuses on novel assessments of climate-related exposures and their impacts on health. His talk today is titled "Tropical Cyclone Exposure is Associated with Increased Hospitalization Rates in Older Adults." Robbie, whenever you're ready. Robbie, I think you may be on mute.
Hi, can you hear me now?
Yes.
Okay. Sorry, one sec. Sorry about this. Just a second. Okay. You can see my screen? Okay. Hi, thanks, Brooke, for the introduction, and it's lovely to be with you. I'm just going to go over some results from a recently published paper that involved quite a few of the colleagues who I'm on the panel with. So without further ado, I'm going to go straight into it. So as a brief background to this paper, hurricanes and other tropical cyclones have devastating effects on society, and limited studies have quantified their impact on some non-fatal health outcomes. However, previous assessments of health impacts have largely focused on single extreme events, including well-known examples, as previously mentioned, such as Hurricane Katrina and Sandy. So there was a clear research gap in comprehensively categorizing the impacts of tropical cyclones on hospitalizations. So what were the aims for this particular study? Our aims with this study, therefore, were to characterize the impact of tropical cyclone exposure on hospitalizations from various causes in the United States in an older population, and to identify effect modification by classification of tropical cyclone and type of hospitalization. First, a discussion of the data we used, which we used Brooke and colleagues' hurricane exposure data packages. So our study population was Medicare enrollees with a total of 70 million hospitalizations during our study period of 1999 to 2014, so 16 years in around 900 counties from 30 states, which experienced at least one tropical cyclone day during the period. And you can see the total hospitalizations over time on the plot on the right. We assessed health outcomes from hospitalizations using ICD-9 CM codes to create county level cause-specific hospitalization counts, and divided these causes into 13 meaningful and exhaustive groups, including cardiovascular diseases, injuries, respiratory diseases, cancers, and several others. For our exposure for tropical cyclones, we classified exposures as having winds greater than the Beaufort scale gale force wind speed, which was greater than 39 miles an hour for tropical cyclones. And you could see the map on the right, total tropical cyclone exposure counts for daily by county, and integrated across the map, there are around 2,500 tropical cyclone exposure days in those counties. And so for further analysis, we further separated exposures in counties of greater than 73 miles an hour for hurricane exposure. So onto our statistical model briefly. We analyzed the association between daily hospitalization rates and tropical cyclone exposure by applying a conditional quasi-Poisson model. This approach examines contrast within matched strata, similar to a case crossover study design in a computationally efficient way. In this case, we only compared counties to themselves on equivalent days of the year in previous or in other years. And by doing so, we only examined contrast within those matched strata, and so therefore controlled for non-time varying factors varying across counties in our analyses, as well as seasonality. To quantify the association between daily hospitalization rates and tropical cyclone exposure, we included unconstrained distributed lag terms for up to 7 days after exposure. We also flexibly adjusted for longer term time trends, mean temperature on the day of tropical cyclone exposure, and particular day of the week. So that's a brief overview of the model. Let's discuss a few result slides briefly. So we analyzed the percentage change in hospitalization rates associated with tropical cyclone exposure. So to the right of 0 is an increase in hospitalization, and to the left is a decrease. And we did this by days after tropical cyclone exposure, up to 7 days after the day of exposure. So on the y-axis, the 0 is the day of tropical cyclone exposure, down to 7 days after tropical cyclone exposure. And I'm going to highlight a few examples. So first, for respiratory diseases, we observed the highest overall increases in hospitalization rates for respiratory diseases overall, actually, and increases occurred across all study days after the day of exposure, peaking 1 day after exposure with a 24% increase. And one likely explanation for the elevated rates in respiratory hospitalizations following cyclone exposure is that those with respiratory issues may need power for medical equipment to breathe, which compels them to visit a hospital when power fails. But there are many other particular reasons also. And next, for injuries, injury hospitalization rates increased across all study days after the day of exposure, with a peak 2 days after the day of exposure. And injury hospitalizations are impacted by tropical cyclone exposure, both directly and indirectly. So during and immediately after tropical cyclone exposure, common injuries originate from transport accidents and structural collapse of buildings. Days after, other injuries such as puncture wounds and burns may take more prominence in hospitalizations. For cardiovascular diseases, we observed decreased hospitalization rates on the day of exposure, peaking 2 days after exposure. gradually returning to the rate expected during unexposed days within about a week after, about 7 days after. And other causes I'll just briefly show tended to follow the same pattern as cardiovascular diseases, as highlighted in black, but I won't go into very much detail there. So decreasing on the day of exposure, peaking 1 to 3 days later, and gradually returning to the rate expected during unexposed days within about a week. I'll come back to this pattern a little later. So we've seen a broad causes. Let's have a look at a preview of sub-causes. We also studied over 100 sub-causes of hospitalizations as subsets of the 13 mentioned broad causes. And here I'm going to present average percentage changes in hospitalization rates across the days after cyclone exposure, which again, to the right of 0, an increase, and to the left, a decrease. So in essence, what's the average effect over the week after tropical cyclone exposure? And on the y-axis this time are different subgroup causes grouped by main cause. I'm going to take an example to talk through, as there are over 100 subcauses in the study. I'll use cardiovascular diseases. So while cardiovascular diseases did not change overall in the week, that's what we found anyway, there was a variation in changes to hospitalization rates for subcauses. So here you can see the subcauses for which hospitalizations increased, with acute myocardial infarction highlighted here. In contrast, the following subcauses decreased, with heart valve disorders highlighted here. And these subcauses were largely divided up into emergency or acute causes of hospitalization increasing, and non-emergency or chronic causes of hospitalization decreasing. So I'll briefly show you the entire set of subcauses in the figure now. And so while in the interest of time, I'm not going to suggest we look at everything. We did notice the broad dichotomy into emergency and acute increasing, with non-emergency and chronic decreasing. So I'll have to go through those quickly. So in addition, we examined the distinct impact of tropical cyclone exposures, in which the county's peak sustained wind was hurricane force compared to tropical cyclone. So hurricane in purple, and gale to violent storm. So tropical cyclones of lesser but still powerful winds. We looked at the effect modification here. And again, to the right of 0 is an increase, and to the left is a decrease. So the next set of figures, once again, we've got lag day again on the y-axis. So 0 to 7 days after tropical cyclone exposure. And I'm going to use respiratory diseases as the main example here. And across categories, you can see here that broadly the purple is amplifying the effect of the orange. And what that translates to is that hurricane impacts hospitalizations to a much greater degree than less powerful, but still powerful nonetheless winds. But what's also interesting is that the orange ones are still have an effect. So less powerful winds are of interest here. And so I'll just briefly show the entire figure. And you can see that that pattern is broadly repeated throughout respiratory diseases and injuries here, and other such ones. So in the interest of time, I'll continue on. We examine the modifying effect of type of hospital admission as well, emergency and non-emergency, with the same structure of the axes from the previous slides appearing here. So I won't go into that again. So from our example of respiratory diseases, we can see the difference between emergency and non-emergency hospitalizations on the day of tropical cyclone exposure, with non-emergencies going down and emergencies increasing. And it's similar for injuries. You can see it's clear that increases are first driven by emergencies, and then decreases driven by non-emergencies. And so once again, you can see that this effect continues over other causes, which I won't go into, but you can see in the paper. And so just as a summary, tropical cyclone exposure we found is associated with overall increase in hospitalizations for many causes and sub-causes, decreases for some non-emergency or chronic conditions. Hurricane force tropical cyclone exposure amplified the effect of weaker winds. The impact was less strong for tropical cyclones of weaker winds still remained. Hospitalization rates where increases were driven more by emergencies, decreases were driven by decreases in non-emergency hospitalizations. And things to think about: acute versus chronic, different kinds of effects and how they're biological or behavioral. And so this is just a first step, but there are other things that would be fascinating to look at that I hope to with other colleagues. So I'd just like to thank people briefly, and thank you very much.
Thank you so much, Robbie. If you have any questions on Robbie's talk, please put those in the Q&A box through the Zoom menu. Our next speaker will be Dr. Rachel Netherly. She's an assistant professor of biostatistics at Harvard T.H. Chan School of Public Health. There, she developed statistical methods motivated by applications in environmental and climate epidemiology. Her talk today will be on integrated causal predictive machine learning models for tropical cyclone epidemiology.
Thank you, Brooke. Robbie, can I get screen share privileges? I think you're still sharing yours.
Yeah. Sorry, I'm just trying to stop.
Oh, that's okay. Take your time.
Yep. Yeah, got it.
Perfect. Thank you. Okay. So you guys are seeing my screen now?
Yes.
Perfect. Yeah, thanks to Brooke and Greg and all the others who have dedicated a lot of time to organizing this. I've learned a ton already, so looking forward to the discussion later too. So I'm going to talk a little bit more about the technical biostats side of things. So apologies in advance to anyone who's bored by that. I think as a lot of the previous talks have also highlighted, a lot of the past academic work, at least on tropical cyclone epidemiology, has really focused on quantifying the health impacts of single storms, so sort of case studies, or it's focused on, like Robbie's paper, quantifying the average health impacts across a lot of different storms. We know from the literature that individual storms can have really heterogeneous health impacts. So single storm epidemiology, while super important, often doesn't generalize well. And then the same sort of idea with sort of looking at averages across storms, super important, but it's a little bit too coarse to be able to be useful for strategic targeted disaster preparation. So the goal of the project that I've been working on is really to try to produce high precision tools that allow us to understand both the heterogeneity and the common patterns in tropical cyclone epidemiology in a way that can hopefully inform disaster preparedness and mitigation efforts. So thus far, we've been interested in several aims. So first, we've been working on trying to standardize estimation of acute health impacts of tropical cyclones or tropical storms. I'll use those interchangeably at high spatiotemporal resolution. So we want to basically learn how to estimate the effects of tropical storms in a way that can be generalized across storms. And then we want to identify unique patterns of health effects that are common across storms, and then those that are unique to particular storms. So finally, we'd like to use this information that we learned to be able to build models to identify communities that are at highest risk for future storms. So to do this, we've been trying to develop what we're calling causal predictive machine learning models. And these are sort of big models that contain both a causal inference and a predictive component. So why do we need both to accomplish these aims? Well, our first aim that I mentioned on the last page is to estimate health impacts of past tropical cyclones at high resolution. So I think that's clearly a causal inference task. And when doing that, we need to make sure that we adjust for confounding and all the classic things. We also want to capture both direct and indirect tropical storm health effects. But then our second two aims from the previous page, we're really looking to identify drivers of heterogeneity in tropical storm health impacts. So more formally, we might want to be able to relate a tropical cyclone's health impacts to its meteorological features, as well as the features of the communities that it affected. So this is really more of a descriptive or a predictive modeling task. However, if we are going to use the health impacts that are estimated in the causal inference piece of the model in the descriptive piece to be able to better understand relationships between health impacts and other features, then we really need to formally link these two components of the model so that we can properly account for uncertainty that arises from both of them. And so that's our reasoning behind developing these integrated causal and predictive models in this context. So in this work, you can basically think that I started with a data set that's almost exactly the same as the one Robbie described for his work. We have all Medicare deaths and hospitalizations for the period 1999 to 2016. And we've linked that with county level tropical cyclone exposure from Brooks' package for the same period. And so before I introduce the causal model here, I think it's helpful just to visualize the data structure that we'll rely on. So for now, let's focus on a single tropical cyclone and a single health outcome in the Medicare population, like deaths, if that's the easiest thing to think about. So first, we're going to structure the health data surrounding the time of the tropical cyclone into what we call a panel data matrix, which is sort of like a multivariate time series. So in this case, for all the counties in the eastern US, we create a time series of their rates of whatever health event we're looking at, covering a time period that starts well before any of the counties were exposed to this particular tropical cyclone and extending to a short period afterwards, whatever period that we want to look at health effects over. In our case, we use 2 weeks afterwards. So in this way, we create this type of tropical cyclone specific panel data matrices, and these are going to be a key part of the causal inference piece of our model. So I think many of us probably already know that the sort of standard way of estimating health impacts of tropical cyclones is to use what's known as an excess deaths analysis, or for more general health outcomes, an excess event analysis. So in the simplest case, these sort of excess death analyses just estimate an expected number of events that would have occurred in the absence of the storm in the storm affected areas using data from the same period in previous years. And they compare that expected number of events to the observed number of events that occurred during and after the tropical cyclone exposure. So that's kind of a simple way of answering what I'll call a counterfactual question of how many adverse health events would have occurred during the storm period in the absence of the storm. And then of course we can compare that to the number that did occur during the storm. And the most notorious example of these types of analyses is the high profile ones that were done for Hurricane Maria. In the causal inference piece of this model, we're going to be actually answering that same question, just with a slightly more sophisticated statistical approach. And we're also going to be able to do it at high resolution. So let's start back with our panel data matrix for a single tropical cyclone that I introduced a couple slides back. The first thing we're going to do is remove or set to missing the observed health event rates for exposed counties during and after the exposure. So these grayed out boxes here. So then we're left with a matrix of only health outcomes that occurred in the absence of tropical cyclones. And we basically treat those observed outcomes in the exposed counties during exposure as missing values that we want to impute. So at a high level, what we're really trying to do here is estimate outcomes that would have occurred in the absence of the storm in storm affected areas. And our model is doing that roughly by comparing trends in health outcomes in both exposed and unexposed counties prior to the storm, and then using that information along with trends in the unexposed counties during the storm exposure time to project the number of events that would have occurred in exposed counties absent exposure. And formally, the model that we're using to do this is a latent variable model called matrix completion. It's similar to factor analysis for imputing missing values in a matrix. And we've extended this model here to accommodate count or rate outcomes. And a major benefit of this method is that we don't need to worry much about adjusting for confounding, because under pretty mild assumptions, the factor structure of this matrix completion method makes the model able to adjust for time varying unmeasured confounders, which is a pretty sweet guarantee. This model also allows us to do estimation of the excess events for each county separately. So it gives us that high resolution inference that we were looking for. So then what we're doing is we're applying this approach for each tropical cyclone separately and getting estimates of the health effects in each county for each tropical cyclone. And then for the sort of descriptive or predictive component of the model, the second component of the model, we're passing those health effect estimates from the causal models for each tropical storm over our entire study period into a predictive model. And in this model, the estimated health impacts of the tropical cyclones are actually going to serve as the outcomes. And we're modeling the relationships between those estimated health effects and the meteorological features of the storm, as well as the socioeconomic and demographic features of the impacted communities. And so this model really gives us insight into what features lead to high health risk scenarios with tropical cyclones, which is what we want to know in order to inform sort of strategic preparedness efforts. And the G function that you see in this slide here really can be any predictive modeling tool, something as simple as linear regression or as complex as some fancy black box machine learning model. We found in practice so far that linear models with splines tend to work just about as well as anything. So that's what we've stuck with for the sake of interpretability. And in practice, we wrap both this causal inference and the predictive component into sort of one big Bayesian model. And in that way, we're capturing uncertainties from both pieces. So quickly, I don't have much time to talk about the results we found, but you can check out our preprint paper if you're interested. So we looked in this study at just 4 health outcomes: mortality, respiratory hospitalizations, COPD hospitalizations specifically, and then cardiovascular disease hospitalizations. And so here for each health outcome, I'm just showing the county level estimated health effects for several different large tropical cyclones over the past 20 years. And so this is just the output from the causal component of the model. And so the county level effects, as you can see, are grouped by storm as indicated by these little box plots. And so you can see that the storms that had the biggest health impacts tended to be Katrina and Rita, maybe not surprisingly. You can also see that there tended to be a lot of heterogeneity in the health impacts, both across storms and also within a storm across counties. I don't have time to say a lot more, but there's a lot of rich high resolution information here that you can check out in the paper. And then from the predictive or descriptive component of our model, the biggest takeaway is that maximum sustained wind speed produced by the storm within a given county is by far the strongest predictor of its health impacts, at least for these 4 outcomes, which I think lines up with intuition and what scientists probably would have expected, at least for acute health outcomes. So you can check out our paper on archives. It's a preprint still. And moving forward, we're hoping to improve the predictive capacity of this predictive component, the second component of our model, so that hopefully it can actually be used on the ground to predict county level health impacts of an impending tropical cyclone and identify communities that are at highest risk in advance in order to target them for preparedness efforts. And following Kate's lead, we're also thinking about ways that we can adapt this approach to look at long-term health impacts. Hope I wasn't too far over time.
Thank you so much, Rachel. If you have any questions on Rachel's presentation, please be sure to put those in the question and answer box on Zoom. Our last panelist to speak today is Dr. Greg Cohen. He is a postdoctoral fellow at Boston University Department of Epidemiology. There, he studies the mental health consequences of trauma and the links between social disparities and health disparities. His talk today will be on hurricanes and population mental health.
Okay, well, thank you so much for the introduction. Can you all see my presentation screen?
Yes.
Great. Okay, so we'll just go ahead and jump right in. And so I'm going to talk today about hurricanes and population mental health. And we'll start out with just describing what are the population mental health consequences of hurricanes. And then I'll spend a little bit of time talking about some strategies to mitigate those population mental health consequences. Okay, so first of all, one of the most common mental health consequences of natural disasters, including hurricanes, is distress. Distress is a common and normative response to this kind of stressor. We also see a fair deal of substance misuse. It might include marijuana, alcohol misuse, opioids. PTSD is thought of as one of the sentinel conditions of exposure to disasters, including hurricanes. And that involves a particular traumatic event, could be the hurricane and the gale force winds, for example, could be losing a loved one, or it could be exposure to an injury or a threat of loss of life. And PTSD involves re-experiencing of that traumatic event. It involves hyperarousal. It involves difficulty with sleep, among other symptoms. Depression is one of the more common experiences following exposure to hurricanes. And finally, prolonged grief arises out of the loss of a loved one and refers to sort of a longer grief period. So let me show you some pictures that will help illustrate the mental health toll of hurricanes. So first, I'm going to start with some really exciting new work on alcohol use disorder hospitalizations. This is in collaboration with Lincoln Laboratory and led by Mark Hernandez, who's an MPH student at BU. And what you're seeing on the left is a highly affected group of counties following Hurricane Sandy. These are located in New Jersey. On the right-hand side, we have a moderately affected group. And you can see on the y-axis, we have hospitalization rate. On the x-axis, we have month. And you can see this Hurricane Sandy landfall going through the center. We can see with the dotted line post that marker of hurricane, the expected trend from the prior 2 years. And then with the solid line, we see the actual. And you can see that the highly affected group experienced a rise in hospitalizations following hurricane. So people within those counties saw greater hospitalization rates. We can see in the moderately affected group of counties that was not particularly the case. When we control for the pre-hurricane trend, we can see that change even more clearly, diverging in the highly affected group around month 6 after Hurricane Sandy. And overall, during that period, we saw about 11.6% more hospitalizations. Now turning to look at post-traumatic stress and depression symptoms. This is data from Hurricane Ike. And you can see on the left-hand side, we have PTSD symptoms. And you're seeing here are essentially growth mixture models that map latent trajectories of symptomatology following the hurricane. And you can see here that for PTSD symptoms, most people actually show a resilient pattern. So even though you can see this is higher than 0, 20 is actually about baseline of no symptoms. In contrast, we see that about 5% have a chronic symptomatology trajectory, about 15% have a recovery, and we have 5% with a delayed trajectory. With depression, the good news again is that most people do okay falling into this resilience category. It's about 60%, but then we have about 10% with a delayed symptomatology, about 21% with a recovery, and finally we have about 10% that are in this chronic trajectory. So what are some of the predictors of different trajectories and of symptomatology persistence? Looking at a study of Hurricane Katrina, this graph is showing you the proportion over time with continuing PTSD symptoms. So this is essentially giving you a marker with these Kaplan-Meier curves of how quickly different exposure groups are recovering. And on the x-axis, we have time from Hurricane Katrina to PTSD remission. So the first observation came at about 6 months during this study. And we can see that hurricane-related traumas that include things like being physically injured or killed, seeing dead bodies during or after the hurricane are related to a longer course of PTSD symptoms. So too are hurricane-related stressors, where we see an even greater effect. And some of these stressors include shortage of food or water, displacement from home, loss of sentimental possessions, and so on. And then finally, hurricane-related financial losses are also a risk factor that seem to independently predict course of PTSD symptoms. And this is an area that I think is only increasing in importance and gaining steam over time. So now, how can we mitigate the population mental health effects of hurricanes? So some of the work that I've done took an approach looking at comparing different health service models. So on the right-hand side, we have a model that we call usual care. And this is a treatment that focuses on skills training and also supportive counseling. And this is what is often rolled out in the context of many natural disasters and specifically hurricanes. It's called Skills for Psychological Recovery. So that's what most cities do, and that's what New York City did following Hurricane Sandy. And we said, let's take an alternate approach and look at this idea of a stepped care model, where essentially we're just going to use a simple algorithm to find cases. And if people are assessed as positive for post-traumatic stress disorder, which was the outcome of interest in these studies, we're going to offer them cognitive behavioral therapy, which is a treatment for people who have reached clinical levels of mental health service need. If they don't screen positive for PTSD, we're going to use our lower level treatment of Skills for Psychological Recovery. So in order to implement the study, looking at different modes of treatment, we used a simulation framework. So we can create virtual worlds through simulations. In this case, we used agent-based modeling. And this virtual world takes data that we know, data that will give us some measure of causal effect of different components of our model. We can create that virtual world, and then we can run some experiments where we vary the treatment modality in this case. And then we can take that information back to the real world and see if the findings hold up. But this will give us a proof of concept. And so we ran a simulation model looking at the usual care that I described earlier compared to stepped care, which is a case finding and a more targeted treatment paradigm. And we looked over 2 years following the hurricane. What we found was that at about 6 months, we saw a divergence between stepped care and usual care. That divergence expanded from about 10% to about 30%. These are all just giving you percentages of difference in the recovery rate from PTSD. And that persists throughout the rest of the study with a pretty convincing effect. The next study that we were interested in doing was taking the focus into a bit more of a particular population, which is to focus on helping out people who are economically vulnerable and may have experienced property damage, temporary displacement, and income loss following the hurricane. And we decided we wanted to create an additional intervention component that we called social services case management. And social services case management involved the in shelter. So these are for people who are specifically have been in shelter. We're going to offer them referral to mental health services, and we're also going to offer them temporary loans to get back home sooner than later. So we went ahead and we implemented that model, adding it onto our stepped care compared to usual care model. And within each of those stepped and usual care, we added one variation, which was the social services case management. You can see this is showing you cases of PTSD remitted per 100 on the y-axis. On the x-axis, we have time since hurricane. You can see that the stepped care with and without social services case management diverged starting around 28 weeks. We saw that continue throughout the simulation. And then we can also see that usual care with and without social services case management diverged starting around 52 weeks and continuing on through the simulation. I will note that social services case management condition diverged much more strongly in the usual care arm of the treatment compared to the stepped care, even surpassing stepped care without social services case management. So just to conclude, mental illness and substance misuse are common after hurricanes, And stepped care does appear to be an efficient approach to addressing post-hurricane mental health and behavioral health needs. And I should add that there appear to be some modifications that can be done to specifically target people who are financially and economically vulnerable. So with that, thank you so much. And I will stop there.
Thank you so much, Greg. We will finish up our discussion today with about 10 to 15 minutes of a panel discussion. So I see if all the panelists will turn their videos back on. And this will be led by Dr. Marianthi Anna Kiormustjoglu, who is an assistant professor at the Department of Environmental Health Sciences at Columbia University Mailman School of Public Health. So I'll turn it over to Marianthi.
Thank you, Brooke. And thank you for, together with everybody, putting this panel together. I did learn a lot as well. I think someone else mentioned that. Very exciting presentations. And thank you to all attendees for joining and attending in a topic that we all on the panel are very excited about. So we have a couple of questions from the audience that will start. And while we're doing this, please feel free to keep posting your questions if you'd like as they pop up. So the first question is more specific to us looking at long-term outcomes, but I guess also potentially it could impact acute outcomes as well. So how do we follow up with the source population properly if they are displaced or if they evacuated? How do we assign exposures to them if they're not there when the hurricane passed because they have been evacuated, or afterwards if they no longer live at their same location? And Kate, I think that was posted while you were talking, so feel free to start and then everybody can jump in.
Yeah, I have a few thoughts, and then I'd love to invite my co-panelists to share their perspectives as well, because I think it sort of depends on what kind of study you're doing. So I think a really important question, especially given that several of the studies that we've described here today involve administrative or secondary data rather than a study design that involves actually recruiting people and following them over time. So I'll give you one example of how this plays out in some of my own work, actually in shorter term work. So I had described in my slides, an analysis that I did looking at the short-term health impacts of Hurricane Sandy in New York City. And the way we did it in this particular study is that we limited people in our study to people who were residing in New York City when the hurricane hit. But we actually, because of the data we were using, we had access to ED visits that were occurring anywhere in New York State. So the good news there is that we were able to include people who might have been exposed to the storm, but then went, say, to Long Island and ended up accessing care outside of the city. What we were missing was cases where people might have evacuated to New Jersey or Pennsylvania. So that's probably a case where even for short-term impacts, we're probably underestimating the magnitude of what's going on. Obviously, the issue applies when you're talking about longer-term health impacts as well, and it can be tricky. I think the answer probably depends a little bit in terms of how you should do it. I think it depends on what you think the exposure pathway might be. So in our case, in the longer term work I've been a part of, we ended up essentially limiting our study to people who were staying in the area around the storm. So you're missing people who evacuated, but that was in part because we thought that the exposures that might be giving rise to asthma exacerbations were exposures that were occurring locally after the storm. So for example, mold in flooded homes or air pollution during cleanup activity. But I think the approach might need to be modified depending on sort of how you hypothesize both short and longer term health impacts might be manifest. So I've been talking for a while. I don't know if my colleagues want to add to that.
Thank you, Kate. Does anyone else have any thoughts about this? Other comments? No, it is, I will say, it is a very good question that we've definitely been talking about it a lot, whether we figure out what to do or not, we'll see. But yes, thank you. And then the next question from the audience is for Robbie, Kate, and Rachel. And it's would non-hurricane related high winds and gale winds still hold for increased emergency department visits and hospitalization admissions? And if so, were any differences observed, if any? So that is, I guess, the pathway. The question is the pathway of the wind itself as an exposure versus what it may represent as a surrogate for a hurricane. And yes, I don't know in what order. Let's go with the order to ask Robbie, Kate, and Rachel.
Thanks, Marianthi. Yeah, that's a great question. And yeah, I guess it depends on what you're using as a hazard. I suppose with high winds, there are going to be causal pathways which still say knock out power or things like that. But there's interesting work. I know other colleagues looking at that here, where looking at the combined hazard of a tropical cyclone or a hurricane, and I know that others will know much more about that than me. But the combined effect being unique to a tropical cyclone in particular, as opposed to just strong winds. But strong winds nonetheless would seem to have an effect if you're taking into account things like down power lines and things like that. So the answer is probably yes and sometimes no. So that's, yeah, thanks.
Thank you, Robbie. Kate or Rachel? Yes, Rachel.
I'll just say that this is something I've asked Brooke a lot of times, I think, and yeah, something that we've talked about before. And yeah, I would say it's concerning to me from a statistical perspective, particularly, if we're choosing sort of controls to do our estimation of what we would have expected this counterfactual, we would have expected the adverse event rate to be in the absence of the storm. If we're picking controls somehow to estimate that, but they were exposed to something that wasn't a tropical storm, but still, involved high wind, would that sort of attenuate our estimates? And I don't have a good answer. Yeah, I would definitely defer to the epidemiologists on this, but I do have statistical concerns about it too.
Thank you. We do have 3 minutes left, so I guess that's time for at least one more question. We'll see how fast that goes, and maybe a second. Is there potential to expand this work to an international scale? All the presentations we heard today were US-based, and how would you expect outcomes to differ in other locations with fewer resources compared to the US? And this is to everyone in the panel. And note takers. So I think there's in general interest, and I think I'm answering for everyone. And I think that there are, not in my group, but I do think there is effort in expanding this work internationally. But I don't know where exactly that is in terms of how near it is to. I will say here that we are all extremely thankful to Brooke for putting together these packages, because it was these packages that allowed the health models and us to be able to run these health models. Otherwise, as you heard from Andrea and James, if each one of us had separately to assess exposures, that we would have never done it. So that means that internationally we also need something similar, and then we can end also health records that are easily accessible. Here we're likely to have somewhat easy access to administrative data set, which might not be the case everywhere else. But yes, I do agree that it does have implications for resources and also for disaster preparedness here versus elsewhere. Brooke and Pat, we have 1 more minute. So if you'd like to close, I guess.
If that's it for the questions, yeah, let me just say thank you to all the panelists for this incredibly insightful workshop. I'm really looking forward to hearing how this work evolves over coming years. This is really exciting. I'd like to thank everybody, and in particular the organizers again, and the people that helped to publicize this. Anything else? Any other concluding remarks from you, Brooke?
No, I'd just like to echo thank you to everyone for attending. I think this is really exciting and interesting research, and it was fantastic to bring together a panel that has folks with a lot of different perspectives on this. Like Pat, I very much look forward to seeing what we can find out in the future years on this topic.
All right, thank you, everyone.
Thank you.